Okay, good morning, my wonderful students. This is our last regular lecture of the semester. So for those of you that are newbies here at UCF, whether it's because you're shrimpy freshmen or because you're transferred up here to UCF, this week is the last week of classes. So you don't have lectures next week. Monday, you don't have Jack. It's officially called study day. So you don't have any classes. You're not supposed to have homework, but you're supposed to study. You get ready for finals. Finals begin Tuesday. And our final is Saturday at 1 p.m. and it will be in this room. All right? Bring your pencil, a good eraser, one of those pink jobs from second grade, your calculator. Bring your calculator. You're going to need it for scientific notation. And better practice up on your scientific notation. Better know how to do calculations using the scientific notation. And unfortunately, it's different for every different kind of calculator. So if you have a TI versus some other calculator, the buttons will work different. So you just got to work it out. You cannot use your cell phone on the exam, so you've got to have a calculator. If you don't have a calculator, actually you can do everything out on pencil and paper. It'll just take you a little more time. But I've shown you how to handle scientific notation on pencil and paper. So you should be able to do that. All right. Now, it is mandatory. You can't, and both sections are going to be going at the same time. So you can't say to yourself, oh, well, I'll just go, I'll miss the exam, and then I'll just go into section 2. But section 2 is going at the same time. They're just going to be down the hall, okay? And I'll probably be part of the time here with you and part of the time down there with them. And so you just got to be here, all right? Now, we're going to have a review set today. I have a few words about physical science to tie everything together and bring it all together. And then we'll break at about 45 minutes into lecture and do a review set. And we have handouts for that, and it will work just like the little mini review, 4 questions that we did 2 Tuesdays ago, and it will work like the final, the clicking on the final. We're not going to have this monstrosity from that we had on exam 3. Okay, here's our cover page. Oh, by the way, next Wednesday, I'll try to put this into the slides for the afternoon section. Next Wednesday, I'm going to have mega office hours. All right, and they're going to start at 9:30 instead of 11 o'clock, and they're going to go until 2 o'clock instead of 1 o'clock. So from 9, so make a note of it. Dr. B study office hours 9:30 to 2. Now, you SSG leaders, if you've already, I don't know how many of you are scheduled during that time on Wednesday, but if you are, it's not a problem because my office hours are going to be so long that if you go 1 hour for your SSG and then slide over to my office hours, you're probably still going to have a good amount of time. So don't worry about that. All right. In addition, the SI review is Monday. All right. And I'll post the time for that in web courses, so you will be able to do that. Now, our SSG signups will start at 7 p.m. I'm pretty sure we're gonna have everything set up for 7 o'clock. All right, and it's a new schedule page, so I put a different identifying image at the top. I can't believe it is not butter instead of the red stapler. So that's your visual key. If you're on the picture, if you're on the page with I can't believe it's not butter, you're on the right page to look at the schedule. And you can look at it now. It's published. And I linked it to the top of our homepage in kind of bluish. And you can look at almost everybody. There's a few people that still need to figure out exactly when they're going to have their SSG, but I think we got about 20 out of 25 set. So you can look at that. Okay, questions about any of that stuff? Do you have a question? Yo. Yo. Can you turn around? I can't get anybody's attention over there. No, don't look around. You. Yeah, you. Raise your hand. Raise your right hand. No, not you. The girl, the blonde-haired girl with the computer open. Right. Did you have a question? No. I saw you raise your other hand. And
I'm sorry, I was stretching.
Oh, okay. Little fake out time for Dr. B. Yeah, okay. All right, yeah, that's why I get paid the big bucks, trying to stay one step ahead of you guys, trying to trick me all the time. All right. Oh, one more thing. Special study group leaders. You know who you are. Please come up at the end of class or when you finish your review set and just coordinate with me for a few minutes and with Darian and Miss Caroline. We have just a few more things to go over before you get rocking and rolling. All right. Now, today we're going to have, I'm going to give you a lecture, but I don't really have any formulas and stuff to write down. So if you want to take real basic notes, just mostly listen and think. Because what we're going to do today for the next few minutes is basically take a look at where we have been. And we're going to walk our way or talk about our journey up to the top of the mountain where we find ourselves right now at the end of the semester. Our operation here is a small, tiny segment that we could classify in the School of Galileo, the physical sciences. That is Galileo's operation, and we are part of that. We're part of that tradition. You guys are his students now too, and I'm Galileo's student. Just a little bit ahead of you guys, all right? So, lecture 2, and you'll make a note. I have several of the slides today keyed at the bottom right to what lecture. You may want to make a note of that. Lecture 2, remember that we took a look at the spectrum of hydrogen. We used the diffraction gratings because in the School of Galileo, you've got to look at this grand book of the universe. Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics. And hey, you guys, we've done a ton of math this semester. And you guys have been real troopers. I haven't been babying you. We worked carefully and slowly, but I didn't water anything down. And I really gave you a lot of good mathematics. You may not realize it, but I did. Its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. And without these, one is wandering about in a dark labyrinth. But we are not in the dark labyrinth now. We're up on top of a mountain. And if you've ever been on top of a mountain, you know that once you get up there, you can see forever, as the saying goes. All right. This is the first topic that we talked about. Getting from point A to point B. And very simple, velocity, speed times time. We talked about the right triangle that you can use to calculate a distance in 2 spatial dimensions, in 3 spatial dimensions. And then we diversified, getting from point A to point B. Okay, you got to know how far you're going. But also the other thing you want to know is when do you get there? So this whole idea of yeah, if you don't want to listen to this, you can be dismissed. It's fine. You can look at this on the YouTube. It's fine. You guys are talking back there, and if it's not interesting enough, you can be dismissed. I don't mind. I really don't. Anyways, the thing that we started the most basic prediction that a scientist wants to make is, when do I get to point B? If I start at point A, and if I, have a certain velocity, when do I get over there to point B? Here's a little bit more deluxe question. When do I get to point B if I'm accelerating? Now here's a picture of a dragster with its chute open. Okay, so let me ask you a question. Is this thing accelerating forward or is it accelerating backwards? Careful. Is the acceleration vector backwards or forwards? It's backwards because it's losing forward velocity. All right? Now, this is another typical thing, and it is not easy. It was not easy for Galileo. But he tackled it, this whole idea of acceleration. Among other places, he tackled it with the famous Leaning Tower of Pisa experiment. I observe a stone initially at rest. Haven't we done that a million times? Study the free fall motion of something initially at rest? Yeah, because we're in Galileo's school. So we're trying to learn from what he did. Initially at rest, falling from an elevated position, continually acquiring new increments of speed. Continually acquiring new increments of speed. That is like the generic definition of acceleration. In fact, Galileo used free fall as his prototype of all accelerations. Okay? It's an easy acceleration. It's a constant acceleration. And he used that strategically. We talked about it in Lecture 4. Another thing that we talked about around that time was dropping something down a well in the mines of Moria, and by Peregrine Took. And to figure out how far something falls when you release it from rest, we had to figure out the distance triangle. Here it is. All right, remember that? 1/2 gt squared. And that's not a position, it's a distance. If we want the y coordinate, we got to put a minus sign in there. But if all you care about is the distance, if you're doing a Cinci problem, just how far is something dropping, just a 1/2 and a 9.8 and a time quantity squared. And our basic idea here is that the area between the velocity graph, which is the tilted line here, below the x-axis, that area forms a triangle, or that graph forms a triangle, the area of which can be interpreted as the distance traveled. And we used that for figuring out the y-coordinate of a parabolic arc as well. A baseball traveling to the outfield. It's based on that same technology. Then we got a little bit fancier. Sir Isaac Newton and the 3 laws of motion. Here's the middle one, second law. A equals F net over m. The acceleration is proportional to the net force divided by and inversely proportional to the mass of the object that's accelerating. All right. Another way to write it is F equals ma. And we talked a lot about that. So Newton's 3 laws of motion, and that was lecture 5 that we got to that on September 6th. So, Sir Isaac Newton. Now, you guys didn't know it at the time, but I knew at the time that we were heading for the top of a mountain. And to get to the top of that mountain, we had to know something about Planck's constant. The one constant to rule them all. All right, so that's coming up, and it actually starts with Sir Isaac Newton. Brandon.
Why do we use net force instead of total force?
Just net force instead of total force is vocabulary. Net force means the total force acting. Yeah, that's what it means. I don't know why they use net instead of total, but they effectively mean the same thing. Good. So to get to Planck's constant, and we know it's up there, we have to get it. You've got to know something about momentum. And my wonderful students, what we talked about is this critical idea that the coin of the realm, in the realm of interaction, is momentum, not velocity, not speed, but momentum, MV momentum. Now, this applies to lovely boxcar collisions. And we were in office hours yesterday. A bunch of students were there, and we were talking about, oh, Dr. B, we were working on some problems from an earlier homework, and one of the students said, Dr. B, if your final was all box cars, I would ace it. So we were kind of messing around with that whole idea. Now, you're probably going to see some kind of a box car or other kind of collision. Oh, I remember why we were talking about that, because we were working on a homework problem from homework, Caleb, what was it, 7? Homework 7? Okay. At homework 7, we were working on that hexagonal molecule, kind of an idealized molecule, and the transfer of momentum and so forth, which is basically, we came to the conclusion in office hours that it was just like a boxcar problem. But it was molecules instead of boxcars. Matter of fact, you can apply the whole idea of momentum exchange, momentum interaction to galaxies or any other object that is interacting. And this is a picture of actually 3 galaxies significantly interacting through the gravitational interaction. Not quite like a boxcar, but definitely you can think of the momentum transfer between these 2 babies. Now, about lecture 7, we started talking about circular motion, uniform circular motion, the Nardo ring. And there it is. Centripetal acceleration, v squared over r. And we started talking about angular momentum. Torques, balancing the seesaw. Right? And you're going to have a review question today about balancing a seesaw, so that'll be good. And why is angular momentum important? Well, angular momentum is important in its own right for objects that are in orbit. But in addition, angular momentum is the unit in which Planck's constant has been cast. So if you think about, the Lord of the Rings and all the different rings that they had, some were cast of gold, some of iron, and the one ring to rule them all. I don't even know what that was made of, but it was undestroyable, except in one place that Frodo got to. And the same thing here, Planck's constant in units of angular momentum. Now, from that, we eventually got up to talking about energy levels. Oh, did I say energy levels? Yes. And did we talk about energy levels with atoms and molecules? Yes. All right, so now you know, thinking back to the free fall of this 2 kilogram bottle, a 2-liter bottle of Mountain Dew, yeah, the reason we worked with those energy levels was because eventually we want to understand atomic energy levels. And then we extended past that. And we thought about the concept of zillions of little teeny molecules and atoms in a gas. And we applied the principle of E pluribus, or what I call the principle of E pluribus unum, to model a gas as a gigantic moles, a gigantic shapeless bulk of zillions and zillions of little molecules that each obey Newton's laws, for which energy, momentum, and angular momentum can be defined and mathematically can be summed up and handled. Okay, and that's the whole idea from which or out of which we get temperature. The Kelvin temperature is proportional to the average kinetic energy of a gas. The pressure is related to the exchange momentum between the gas and the wall of the container that contains the gas. All right, and so that's the E pluribus unum, and that's about lecture 15 on October 11th. A few lectures later, I think lecture 16 was an exam. A few lectures after that, lecture 17, October 18th. Remember this one? Heat, melt, heat. All right? And this was our first really tough brain burner. But you know, you guys, I better make an announcement about heat, melt, heat. In office hours yesterday, we found out that it wasn't just you. It was everybody that I looked at, Cody. A student came in and said, Dr. B, I thought I typed in an answer for number 2 on exam 3 on the clicker question. And I said, all right, let me go take a look. So I dug back down through my data, and you know what? There it was. And he had it right. And then everybody else at office hours, I looked at their data, or I looked for their data for number 2, and yup, it was in there. So I decided, oh boy, I better do this for everybody. So I am going to, if you weren't there at office hours yesterday, I'm going to go down and double check everybody's question 2 answer. And if you have it wrong, nothing will change. But you know, when I went and found Cody's answer, do you mind if I mention your name, Cody? And then a few other students, I thought, boy, everybody's getting the right answer, 6552. So I thought, oh boy, this is a lot of points that are missing. Now, that is possibly going to change exam 3 score for you. Some people, it didn't change the score. But everybody that got those 2 points or 3 points for question 2, it did change their score. Now, it might also change best 2 out of 3. All right. Some people it did, some people it didn't. If it does, nice. Okay. If it doesn't, you haven't lost anything, but at least you know. So you may see that in the next few days, your best 2 out of 3 being revised. By the way, I've been extremely busy with family obligations last week, ever since Thanksgiving. And also, I have a bunch of grading that I still haven't put together, like principally your SSG, but also your clicking roundup. So today's clicking, there won't be any official participation pointage today. So there's no official clicking for participation pointage today. But I do have a bunch of stuff to update. So anyways, one of the things to update was the heat melt heat on exam 3 And, we were doing that October 18th, right after the hurricane. Another thing that we worked on was this whole idea of heating stuff up and what happens to it as it gets hot, like this spy plane, the SR-71 Blackbird, that actually the leading edges on the wings and the nose and the tail fins actually get red hot when it's on maximum afterburner. If it's at the right level of the atmosphere and going maximum speed, it'll actually get red hot. And I've actually seen that myself. And why is that important? Why is this whole idea of heating stuff up to the point of incandescence? It's important because that's what Max Planck was working on when he figured out Planck's constant, the one constant to rule them all. Now, after that, we started talking about waves and oscillatory systems. And I love this picture. Can you imagine surfing on a wave that big? You can't even see the guy. He's like a little dot up there in the picture. Oh my goodness. Prototypical wave phenomena are wavelets and diffraction. The wavelets form here in the barrier opening, and out here on the other side of the barrier, they start curving around, and energy is directed straight down the pipe. That's like the central image that we saw in the diffraction gratings. And then a significant amount of energy is redirected off to the left and to the right. Those are the diffraction lines, the red, the aqua, and the purples that we saw from hydrogen on the first day. And that goes by wavelength. So the other thing that we introduced at about that same time, I forgot to put which lecture this is, but you can look it up, is the whole idea of a phase diagram or a phase portrait. The theoretical or abstract representation of all dynamical states of, in this case, an oscillating system. In a piece of graph paper that has momentum on the vertical axis, P subscript x, and the matching coordinate or the corresponding coordinate x on the horizontal axis. It's not an XY piece of graph paper, although you use the same kind of graph paper to make it. It is abstract, so you can't do Pythagorean theorem with this because you have apples and oranges. But the unit of area of this is important, angular momentum. And here's the energy, and that's basically this formula here is if you took, let's see, if you took Algebra 2, I think maybe, in high school, you might see the formula for an ellipse in this second yellow box. But yeah, angular momentum is important for this. And why is phase space, units of angular momentum? Well, Max Planck, Planck's constant. Are you getting the idea that Planck's constant is important? I mean, I didn't talk about it at the bottom of the mountain, but I'm talking about it more and more as we go higher and higher, deeper and deeper into the semester. Let's keep going. We talked about electrical charge, this mysterious interaction similar to gravitation, but can be repulsive, attractive or repulsive. We talked about Coulomb's torsion balance, the electroscope, and then this problem and problems like this. The linear charge array, the brain burner from another planet, in which we typically choose the leftmost or the rightmost particle and figure out the net force, given some kind of an interaction force between them. And the reason that we were doing that and trying to get a handle on that is so that we could kind of understand what molecules do. And this is kind of an idealized view of a molecule, or an idealized model of kind of a schematic molecule. A real molecule is going to have different shapes and lengths and so forth. So this is kind of a mock-up or schematic of a diagram of a molecule. but still helpful for us to practice with. And that was about lecture 22, November 3rd, just a month ago. Lecture 23, Balmers Series. Remember that? This was the day when we said, there's got to be some pattern. Why are only these specific lines visible for hydrogen, for pure hydrogen anyways, when you look at it through diffraction grating? All right? And then we got H alpha over here at 656, H beta, H gamma, H delta. And these are the two bluish purple. Those are the two tough ones to see, unless you're in a really good lab, really dark and really good clear light. But this whole idea, the observed regularity of the Balmers series, must indicate that there's some unseen regularity in the atom that we cannot see. So this is an important concept. This is kind of like e pluribus unum in a way. We cannot see the atom. We can't go in there and take out a little tiny meter stick or a nanometer stick and measure the size of the atom. But we can figure out the dimensions of the atom by looking at, for instance, the spectra of the atom. And the spectra has the regularity that we find in Balmer's law. And because of that, we are unavoidably bumping up into Professor Planck and Planck's constant, the one constant to rule them all. And why does it rule them all? Because of Louis de Broglie. He said, all right, photons behave like waves, they behave like particles, nice, good. Everybody knows that. But what about electrons? Everybody heretofore thought of electrons as particles, but what if they also have wave behavior? And he said, if you do that and use this formula, lambda equals h over p, to figure out the wavelength of the electron wave, everything works out in the hydrogen atom. It explains everything that can be measured. You know, the red H alpha line, you can figure out, you can distinguish. Matter of fact, you guys, if I had a lab set up here and, I took a bunch, 10 or 20 of you at a time and a few lab setups, you guys could measure the wavelength of red H alpha easily and distinguish it and be able to say, well, it's not 657 and it's not 655, it's 656. You'd easily be able to do it to that level of precision. All right? And all that stuff de Broglie figured out, and it was able to explain by using energy levels, by using Coulomb's interaction, the electrical potential energy that is built into the Coulomb interaction, Planck's constant, and figured out just the idea of constructive interference. And constructive interference enforcing the precise location of certain orbits and no others around the hydrogen atom. The other way to look at it, as I mentioned, was the phase diagram or the phase portrait. And that quantum leaps exist between only those ellipses, only those sets of dynamical states for which the change in the area comes in units of h. That is the abstract way of insisting on quantization, and it corresponds to de Broglie's constructive interference hypothesis. Now, armed with that, we were able to tackle the periodic table. And we've been talking about this for about a week, over a week. All right? And how, everything on the right, the dynamical state of the electrons for everything in the right-hand column, the outermost electron for hydrogen, lithium, sodium, potassium, that outermost electron, the valence electron, is very similar. The physics of all those guys are very similar. And going stack by stack, the second stack, beryllium, magnesium, calcium, strontium, and so forth, the physics of those two valence electrons and the physical properties that they produce are very similar. And that's the insight. Now, Mendeleev, who set up the periodic table, didn't know anything about electrons, but boy, as soon as they did find out about electrons, Mendeleev said, yep, this makes a lot of sense. He must have said something like that. It helps us understand why certain elements all the way on the right in the noble gas column do not really interact. They're just kind of single atoms. They don't really combine and form molecules. You can force them to make molecules, but they're not really that rugged. They'll dissociate quickly. But here's a molecule that we talked about, I think Tuesday, carbon dioxide. And we said, yeah, an atom will try to either empty out its top energy level or fill its top energy level so it has the full complement of electrons, or it strips out a few and completely empties out that top energy level. Carbon in carbon dioxide loses 4 electrons. Well, it doesn't lose them, it shares them. Okay? It shares them with oxygen. And oxygen shares those two. And now oxygen is feeling like a neon. And the carbon is feeling like, well, I've kind of shared out those outer 2, or those outer 4. So now I'm pretty much in a helium-like state. Okay, I've got 2 that are mine, and the other ones are shared out. So, they're here, they're not here, but the 2 that I've got a lock on, they're like helium. And that is what atoms like to do. That is how they form stable compounds. They want to do that. And it's basically based on constructive interference. Covalent bonding especially is a quantum effect. It's basically a result of constructive interference. We've talked about other molecules. Here's retinal. Retinal is the famous molecule in your retina of your eye that when it absorbs a photon in the visible range, it'll flex. It'll extend itself to a higher energy state because it absorbs the energy from that photon and folds out to this extended form on the right. And then after a few seconds, it'll migrate back down to its lower energy state. That's the transformation B, back to the folded state. Okay, and that's what happens with your eye. And all that is described by starting with Louis de Broglie and all the other quantum physics that we've built up from that. And we've mentioned other molecules through the semester. For instance, DNA. Now over here, you might want to make a note of this one. Photo 51, this is the famous photo that was, it's an X-ray diffraction image. Okay, so it was taken on film using X-rays, so X-ray film. Just kind of like what you use for looking at broken bones if you broke your arm or something like that. And it is the image that was taken in the late 40s or early 50s that allowed Watson and Crick to, when they saw that, they realized that DNA was a double helix. And everybody was trying to figure out, like all the famous chemistry and physics people were, that had an interest, so not astrophysicists, but, a lot of chemistry and physics people were trying to figure out DNA. But nobody could figure out its structure. They kind of, well, it looks circular, but it's. And so these guys saw this famous image 51, photo 51. And actually they didn't take it. They kind of kiped it. They well, what they call midnight requisition, 5-finger discount. Somebody wasn't nobody was looking. They went in and looked at these images that they weren't supposed to. And although somebody else, the woman who took this photo got ripped off, really. I should have put some additional reading about that. But she didn't get a Nobel Prize, and those other guys did, but she's the one that got this photo. And anyways, the double helix structure, yeah. Valence electrons interacting, all different kind of atoms, carbon, phosphorus, all the different atoms that make up DNA. So now we've finished our discussion for the moment of our topic, which was to get to the top of the mountain and look at the compounds and the structure of the periodic table by using, among other things, Planck's constant. But I don't want to end with Planck. I want you to think about one more thing. All right? So we're up at this mountaintop, and let me just give you one more image, and maybe you want to take a note about this. Slide number 45, December 1st, 2016. Dr. Brickner, a guitar and a little slice of DNA. A guitar and a little slice of DNA. The DNA has a structure that's basically controlled by constructive interference for electron waves around all those atoms. And those are actually submolecules. The DNA molecule is made up of a bunch of other molecules. Pyrimidine, purine, and deoxyribose. All those different molecules. And you studied those things in high school biology, I guess. Thymine, adenosine, and a guitar. A guitar. A beautiful guitar. Justin. No. What's your name again? The guitar man. Troy. Troy came up and played guitar for us. Now, you may have been thinking on that day that Troy, Dr. B is going on about guitars and stuff. It's boring. You know. But I knew on that day that this day was coming. That I would want to compare complex molecules like DNA to a guitar. The tones that are produced on a guitar, on a single string, are controlled by constructive interference, standing waves. Right? Wavelets form at the endpoints of the string and they ricochet back, they interfere, and only certain wavelengths will survive and resonate. And that is the wavelength and its accompanying frequency that you hear, and only that tone. 6 strings on a guitar, all of them tuned. Each one has a frequency, and if you strum the right strings together, you get a chord. Right? Chords. Several strings together. That it sounds great. And if it's detuned the way Troy did, it sounds sour. It's like fingernails on chalkboard. You can do it. It's not recommended. Somebody with do you have perfect pitch? Okay. So if you have perfect pitch and you hear something that's off tune, it's bad. It hurts. Okay. A chord, several strings simultaneously. Sounds great. A molecule, several atoms, each atom having energy levels controlled by constructive interference. And each atom partnering up with other atoms also constructively interfering, and together those strings, oops, did I say guitar strings? No, I meant those atoms make DNA. Or water, simple molecule. 3 strings, two hydrogen strings and 1 oxygen. The energy levels controlled by constructive interference, just like a guitar. The tone of the chord you hear, controlled by constructive interference, and only those tones, if it's been tuned and everything. So when Troy was up here doing this demonstration with his guitar, he provided for us an image of how you can think of a molecule. A molecule is like a guitar. DNA is like a guitar with zillions of different strings. A piano, 88 strings. Guitar, 6. How many does a violin? Anybody here play violin?
4.
4 strings on a violin? Okay, so 4 strings on a violin, 6 on a guitar, 88 on a... I don't even know what kind of... I don't even know if anybody can count the number of atoms in a DNA molecule.
4.
No, it's not 4. It's more than that. 4 times some big number. So what I want you to think about, DNA is the best one to think about because DNA is the molecule of life. And you're alive. Matter of fact, you have zillions and zillions of different molecules. So you don't just have a guitar, you've got a piano, and you've got a violin, and you've got a zillion other instruments. So you, walking around, are the best symphony of them all. Isn't that nice? So think of yourselves in that way. The best symphony that you can ever hear. Us. All right. We've finished the semester. And for us, for all of us, it's just the end of the beginning. We've just done the cover page and the title page. But for all of you, there's a really, really good story ahead. If it's really true about the symphony. And so I wish everyone well. And I thank all of you for being my students this semester. Now, let me pause the podcast. Get my cursor here. There we go. You're going to have a mega review homework this weekend. and SSG signup. So don't forget about that.